buenos días a todas y todos. Es un gusto estar aquí hoy para tener una nueva sesión de los Inria Chile Talks. En esta oportunidad tengo un placer enorme de presentar a un colega de muchos años. Tuvimos la oportunidad de trabajar juntos, a Juan Gómez Romero, que es un tremendo investigador español. Coincidimos en la Universidad Carlos III de Madrid, en los primordios de nuestras carreras y bueno, Juan es actualmente un catedrático del Departamento de Ciencias de la Computación e Inteligencia Artificial de la Universidad de Granada. Trabaja desde entonces y aún continúa trabajando en inteligencia artificial y aprendizaje automático en muchísimas áreas, pero sobre todo en la parte más de eficiencia energética y en cómo caracterizar toda la parte de desinformación. Es además codirector del laboratorio SAIL-UGR y del equipo de investigación de la Universidad de Granada en el proyecto IA4TES, que es Inteligencia Artificial para la Transición Energética Sostenible. Y anteriormente, efectivamente, y aquí fue donde coincidimos, fue profesor de la Universidad Carlos III de Madrid y también investigador visitante en el Data Science Institute del Imperial College London. Así que, de nuevo, es un placer enorme tener aquí a Juan, que nos va a presentar la charla Modelado de Sistemas Físicos con Redes Neuronales. Es un tema súper interesante y también que está muy en línea con varias líneas de investigación también de Inria Chile. Así que, bueno, feliz, tienes una audiencia parte presencial acá en Inria Chile, pero tienes una gran parte también conectados en línea, así que espero que disfruten de la charla de Juan y que aprovechen y le hagan muchas preguntas ahí al final. Voy a dejar después a Luis para que modere esta parte de la sesión de las preguntas. Así que, Juanito, de nuevo, un honor tenerte por acá. Gracias por aceptar la invitación y es un lujo tenerte aquí en la instancia esta de los Inria Chile Talks. Así que eso, gracias.
Muy bien, muchas gracias, Naya. Para mí todo un gusto reencontrarnos después de bastante tiempo, no vamos a decir mucho ni cuánto, y bueno, seguir en la brecha trabajando en estos temas tan interesantes como el que os traigo hoy sobre modelado de sistemas físicos con redes neuronales. Voy a pasar a compartir la pantalla y si os parece, comienzo la presentación. La presentación será en inglés y después, bueno, pues preguntas en español o en inglés según el modelador estime conveniente. Now in English. Good morning, good afternoon. It's for me a pleasure to participate in this talk. Today it was surprising, but also pleasant to find in my inbox an invitation for this series and to see that after quite a long time, me, myself, my group, and also your group there, Luis, Nayat, and all the researchers at your institution we're sharing this interest for combining physical systems, neural network, and trying to simulate complex behaviors in real systems. As Nayat already said, I'm co-leading the Sustainable Artificial Intelligence Laboratory here at the University of Granada in Spain. We are more than 12 researchers in modeling, control, and optimization of cyber-physical systems, mostly with an interest on energy efficiency. We have other different research lines in the laboratory, but this one is most related to the topic that we are addressing today. We are working on different projects. We have a quite big project on energy and artificial intelligence, which is this AI for TES. And we have also two sister projects more focused on building simulation models for buildings, which is this synergy project, and also another project for the construction or simulation models from data in general in different setups. So in this presentation, I will not explain very much the technical details of our works, nor the technical details of the techniques that we are using, that we are developing in these research lines. I would like to give you a few hints and, well, provide you with a tour on the many, I would say, many mistakes that we made in this through this path, and also a few lessons that we have learned from this research. I will begin with the motivation of our work, and then I will proceed with the fundamentals and some specific techniques and applications in the area before concluding the presentation. Well, in 2020-21, in our group, we were thinking about well, what we can do to simulate, to know better the functioning of physical systems, so to speak. So we proposed this schema, which is a quite simple or even naive approximation for a general formulation of data-driven simulation models. That is, simulation models that are built not from the physics of the system, but from data collected from the observation of the systems. Our interest was not exactly the simulation models, but the development of surrogate models which were useful for learning control for these systems. At that time, and also currently, we were working on reinforcement learning, and as you may know, this control or this machine learning paradigm for control is based on collecting observation from an environment and also acting on this environment, then evaluating how good and bad are these actions based on a reward function. And this reinforcement learning was mostly applied to building control, to heating, ventilation, and air conditioning control in these buildings. We were performing, well, to train one of these agents, we need a lot of interactions with the environment. This is not feasible. We cannot interact with the building continuously and try different control strategies without bothering the occupants of the buildings. So we used at that time physical models of the buildings, models based on heat transfer equations, and well, we can say that these are classic simulation models for buildings. But if you want to perform many simulations, if we want to train our agents in the simulation environment, we need to interact with the environment. This is with the simulated environment. This is better than interacting with the real system, but it also it can take quite a long time to run simulation. So this is why we started thinking about how we can speed up the simulation and how we can try more or different configurations for our control agents, and also how we can test different algorithms in this regard. Well, one step back, let's talk first about the fundamentals of physical systems and simulation of physical systems. Usually we're interested in complex systems, which are those that can be described with partial differential equations. Usually we define this kind of differential operators, this F here, which is an operator parameterized by lambda, And this operator applies linear or nonlinear and differential operations on U, which is the solution function that we want to find. For example, for a simple use case, which is heat propagation on a one-dimensional road with initial conditions, our system needs to satisfy the heat equation, which is this one here, which describes how the temperature values on the rod evolve in time. So the differential in terms of the differential operator, we can have this expression here. We can equal this to 0, and well, for this simple case, these equations have a solution, which is this one here. The specific values numbers are derived from the initial condition, but essentially we can express a solution U for these equations in this way. This is actually the example that we use in this paper here. I will talk about this paper afterwards. Regarding neural networks, well, this is even more well known in the computer science area. Neural networks can help to approximate complex functions. Neural networks consist of layers of neurons, like the ones that we have here, and each one of these layers applies a linear transformation and then a nonlinear activation function on the input data. Training these networks mean adjusting the weights of the network in order to minimize the error. That is the difference between the output of the network and the output, which is known for many examples or many samples of the input values. These neural networks are typically addressing supervised learning setups. So, in order to modify the weight of the neural network to fit the output to the non-outputs, we apply a combination of gradient descent and backpropagation algorithms. Essentially, the modifications of the weights are proportional to the derivative of the loss function with respect to these weights. Neural networks can be programmed with the typical libraries like PyTorch, which is mentioned here, also TensorFlow and Keras. Broadly speaking, these libraries are more than neural network libraries. These libraries are actually focused on automatic differentiation. Automatic differentiation is a technique used to compute these gradients, this derivative efficiently, and to minimize this loss function by changing the network weights as mentioned before. So automatic differentiation frameworks like PyTorch, as I'm showing here, can help us to define a graph, a computation graph with operations. These operations are arranged in a direct cyclic graph, like this one here. And with PyTorch, we can define the graph. We can define the last step of the graph, this loss function, and then we can apply or run a forward pass, which is calculating outputs from the input, and we can also compute gradients by applying backpropagation from the output to the input. And this, well, in this case, this graph corresponds to a very simple neural network, but this computational graph can be anything, in the sense that if we have here differentiable operations, we can calculate the output of the operation, but also compute the gradients of the operations by differentiation. So to set things straight, and coming back to simulation of system, we have numerical methods to solve differential equations. These are well-known techniques. They are precise, but they are also hard to define, and the computation is slow. On the other hand, we have prediction with neural networks. We don't need to explicitly model the underlying phenomena. Neural networks are slow to train, but they provide fast inference, and they don't need a physical model. But usually they require tons of data to perform well. They are prone to errors, and also the stability of the models against minor variation of the input is well, it's not very good. So from all this background, we have this kind of hybrid approaches for physics-based machine learning emerge. There are two main variants for physics-based machine learning. One of them is directly based on this differentiable programming in these differential graphs that I mentioned before. In this case, we can define a computational graph of the operations defined in the differential operator, and we encode the differential equation. For example, in this case, we have this equation which represents the loss function, so we can encode in the neural network, or in the computational graph, more specifically in the computational graph, we can define the operation, we can define this loss function, and we can minimize this loss by applying differentiation on the graph. The second approach, and this is the one that we are going to revise in this presentation, is in general neural network regularization. In this case, what we do is to incorporate to the loss function of the neural network an additional term with the residual of the partial differential equations. This is the typical setup for pins, which I will explain later. In this case, we have, let's say, the typical error of the neural network, which would be this term here. Here we are calculating this term by subtracting the output of the network with a given set of weights, theta with the expected output of the with the real output of the samples, and here we have another term which is related to the partial differential equation. This setup is actually the formulation of these pins, which are the most common and the most widespread form of physics-informed neural networks. These pins are a family of neural networks that are trained to solve supervised learning tasks while respecting the laws of physics described by partial differential equations. Essentially, this loss function here is the same that we had before. We have a neural network which is, more broadly speaking, we have a computation graph with one section here, which we are calling F1, which is the graph corresponding to the partial differential equation with the formulation that I presented before. And we have a second, let's say, half of the neural network, which is classic neural network, in particular a feed-forward neural network. The output of these two sections of the graph are combined. Well, here I'm just using addition for the combination, but we can have different weighted combinations, or even we can define another neural network for with weights for this combination. Eventually, what we have is this output G here over this G. The loss function is calculated, and then the neural network as a whole, or the graph as a whole, is trained. Is the weights are adjusted by making or by performing back propagation and gradient descent and back propagation from this J. These pins are this formulation is the one proposed by Racy and collaborators in 2019, and this is the one supported by frameworks like SAIL, which is a framework in Keras, in TensorFlow, for defining these pins. On the right hand side of the slide, we have an excerpt of the implementation of the pins with cyan corresponding to the previous example on the heat propagation on the 1D rod. We can define the symbolic model with typical NumPy operations. The equation that we have there is encoded in this function here. And then we can define the model elements in cyan. We have variables like x and t, and we have the functional u over x and t. And then, well, here we are also providing the shape of the output and also the activation function for the intermediate steps of the computational graph. We can define the grid, the surface over on which we are placing the points for which the symbolic model will be calculated, and also it can correspond to the sample points that we have for training. We can define also the restrictions. In this case, the heat equation that I mentioned before is defined as a restriction here with these high-level constructors. And eventually, we can define the model based on these elements, and we can train the model. And the model is automatically trained, and we don't have to manually define the loss function. And of course, we don't have to manually calculate the gradient or even invoke the procedure to calculate the gradient. Cyan is one of the most popular frameworks for pins, but we have also modules from NVIDIA or Deep XD, which have a quite similar setups and constructor for defining the models, and for training the models with the configuration that we had before with this F1, this F2, and all these elements. This formulation of physics in 4 neural networks is quite flexible. It is quite appropriate when we have when we can encode the physical part of the model with the equation, and also when we have enough data from the model to combine both segments or both elements of the network. However, there are also many difficulties or problems with this formulation. We studied these problems in the paper that I mentioned before. We developed this work in 2020, 2021. Well, the paper was published afterwards. Here we identified, we performed different experiments with different use cases and different configurations for the pins. We found that the most relevant factors of training are the structure of the network, the architecture in general, and also the activation functions, with hyperbolic tangent working the best. Nevertheless, we didn't get accurate results for relatively complex problems. They needed these complex problems like extending the heat propagation from the 1D rod to a more complex surface with other heat sources was not working very well. For this, we needed a large and dense mesh with a lot of points and also a lot of computational resources. We didn't find a clear solution for this, except that more complex architectures for beyond the feed-forward network that were used by default with pins were needed. Similar results were found more or less at the same time, but this paper published in New Reefs in 2021, this author agree or also acknowledge that pins fail to address complex problems, in particular those involving diffusion, which were the problem class that we were working with, and they hypothesized that soft regularization introduced by the differential operators made it difficult to optimize the loss. For them, two possible solutions for these problems were using incremental learning, that is, increasing the complexity of the regularizer, starting with simple regularizers with simple PDS, and then increasing the restrictions induced by this PDS. And also they suggested to reduce the rollout horizon. The idea here is to reduce the prediction horizon for the model, and training even different model for different deltas for different evolutions of the systems. This doesn't mean that pins are not useful in general, and also the literature on pins is advancing, and you can find several applications of pins nowadays. In some cases they are successful, in other cases they are not. Probably the most successful setup in general for pins is a situation in which the PDS are not very complex, and also we have either a considerable amount of data, or we can easily generate synthetic data by using these PDs. Relying on these ideas, that is, taking from pins those elements that were working well for us, which were this regularization. In my research group, we have been working in the last 4 or 5 years in the use of physics in general as neural network regularizers, but without following very closely for the initial formulation of pins, and also using frameworks like CIAN, like the CIAN mentioned before. So all this explanation is just an anticipated apology, because in this section of the presentation I will present different works that we have developed in my research group, but that I think that are probably more useful for you if you are working on a very specific problem, and if you don't need this kind of general formulation with PDEs. Also, these problems are simpler in terms of the PDEs than the ones that I mentioned before. Well, the first one is this one about the estimation of building energy consumption. As I mentioned at the beginning of the presentation, we are interested in energy system. One of the first problems that we find in energy system, and particularly in building control, is the estimation of the building energy consumption. This can be made in different ways. We can use this physics formulation here, which is known as energy signatures, and the electrical load of the cooling system, that is the energy that is needed by the heating, ventilation, and air conditioning system is calculated based on the difference between the output temperature, the balance point temperature, which is related to the indoor temperature, and also different coefficients which measure the heat loss in the building. We can also apply pure regression with neural network. We can estimate this electrical load by training, for example, a neural network based on the outdoor temperature, and then we can, if we have enough data, we can approximate this relation. What we are doing in this work is joining these two elements, these A and B models, in the way that we can see in the figure on the right side. This is very, very similar to the configuration of a PIN, but we are not using PIN because we don't have a Ph.D. We have a way more simpler way to calculate, or a way more simple physics model. This hybrid model is what we call a semi-parametric model, and we have found that this semi-parametric model has better results than parametric models, and also better results than not parametric models in general. We are testing this with 18 buildings, and the result of the semi-parametric model, this hybrid model, is in general better than the other approaches. And it is particularly better in buildings for which we don't have a lot of data. If we have a lot of data, like in this case, this is for one building, this is for another building. For this building, we have more data, so the non-parametric model, the neural network, is better than the semi-parametric model. But when we don't have a lot of data, in this case, the semi-parametric works better. Also, this is related to the performance of the parametric model. If the parametric model doesn't work very well, then the non-parametric will be better than the hybrid one. Another example is this one here, is the prediction of power generation by wind turbines. This work is, well, it is a bit more complex than the one before, so I won't go into detail. I just will say that we have a physics-based formulation for this problem. We have a mechanical model of the production of energy, the power generation by the wind turbine, and we can also perform regression with neural network, as in the previous case. So also for this problem, we have proposed a hybrid model, included a loss term based on data, on the regression with a neural network, and also a physics loss, which is based on the physics formulation, the mechanical model of the turbine. We perform different experiments with this configuration, and also we have compared this to a parametric physics formulation, which is in between A and C. Here is this formula here, in which this coefficient can be approximated either with parametric optimization and also with neural network. So in this setup, we perform different combinations, and we find that directly approximating the power coefficient and then the total power from this power coefficient works quite well, let's say, with neural network, without introducing pins or a pin related formulation. In a second iteration of this work, we have studied in more detail where the errors of the pin come from, and then we have proposed an alternative version of these pins, and in this case we have a different combination of the neural network for the estimation of a physics term here, with some variables that are known. This is correct. This is x. Yes, this is just x. From the wind speed, the pitch angle, and the rotor angular velocity, we build a neural network that can estimate the power coefficient, and then we have, on the other hand, another neural network, but in this case to predict the residues, the residuals of P with a global neural network. And then we combine these two terms and find that this configuration works, this hybrid model works way better than the PIN that we had before, and also than other different configuration with the physics model. Well, actually, we're proposing two different configurations for this, and this is the one, the pure hybrid one, the one that works better in this case. Well, enough about self-promotion and our work in physics as neural network regularizers. At the beginning, or at the beginning of the presentation, I mentioned that our first approach was quite naive, because we wanted to build a neural network, pure data-driven neural network that was able to predict from inputs the outputs of the system, the variables of interest of our system. And in this naive proposal, we envision time series method as the most suitable candidate for this estimation, to build this kind of neural network. We were not right, because time series architecture, like LSTMs, for example, were not very appropriate for the problem. But we were right, on the other hand, on a different, we were right, let's say, on the general idea that pure data-driven solution could be useful in this case. The problem there was that we were not looking at the proper architectures. We were looking at this recurrent neural network, but there was another architecture which could be better for this. And this architecture are graph neural networks. Graph neural networks were proposed well, more than a decade ago, but they attracted attention of, let's say, from 2019 to 2020, because they allow processing data different from the typical tabular data different from the typical time series. Graph neural network are intended for graphs. They perform different transformation on an input graph to obtain a transform graph, and then this transform graph can be flattened and fed into feed-forward networks, and then to perform prediction with this data. This proposal here is very similar to CNNs, to convolutional neural network, in the sense that we have connected elements. With convolutional neural network, we have images and we have pixels. Here we have nodes and we have edges between the nodes of the graph. The GNN, the graph neural network blocks, perform operations on this graph similar to the convolutions of a CNN. Actually, they are so similar, they are that similar to convolutional neural network that one of the typical operations on graphs on these GNN blocks are convolutions over the graph. These convolutions over the graph are, for a node, aggregations, weighted aggregation from the values of the properties of the adjacent nodes. And this is performed with weights, and these weights are also learned during the training of the neural network. There are other mechanisms for aggregating information in GNN blocks for graph neural network. One typical or a general one is message passing, in which the exchange of information between the nodes of the graph and then the aggregation is formulated as this message passing functions. Very brief description of graph neural network. The point here, the relevant point here, is that graph neural networks can be used for physics modeling. The proposal of graph network-based simulators, this GNS, was presented in this paper in 2020. And the proposal of this paper states that physical systems can be represented with graphs. In these graphs, the particles of the system are nodes, and the dynamics are modeled as a message passing over the graph. If we have enough data, we can train this kind of networks, and we can simulate the system. We can predict the future state of the system from the previous states. This prediction or horizon can be immediate, that is for the next step, or it can work on a rollout basis, in which the prediction horizon is larger. The architecture used here is a bit complex because it includes an encoder, the processor, and also a decoder. The paper shows that this works quite well for particle system, for example, for fluids, or for other examples are the one that are provided in this web page. If you want more information, I would like to explain more about these graph neural networks, but we are running out of time, so I recommend you this this video, which will be provided as the rest of the slides, in which this paper is explained in detail. Based on the results of this paper, recently the Google DeepMind team published this GraphCast, which is, let's say, an extension of the previous work for weather prediction. They used, again, graph neural networks with this encoder decoder architecture. Now the nodes of the graph represent points over a surface or over a sphere rather than particle. It is interesting that the code of this paper is available here, and if you are interested in this kind of problem, you can check it and you can reuse it. Graph neural networks are a very natural representation for problems in chemical physics. That is, we have molecules, and molecules are graphs with nodes, atoms, and then edges can be links between these atoms. We have applied similar solutions for estimating network potentials of molecular dynamics with water cluster anions, and they perform better than other approximate methods. And also we have applied this to predict some properties of helicins, which are organic compounds with interesting optical and electrodynamical properties. Well, these papers are available, and if you want more information, you can contact me, and I will give you hints about what worked and what didn't work in these cases. Jumping to the conclusions of the talk, I would like to highlight these 4 points here. First one, hybrid physics neural network models can be better than purely data-driven MPDA methods, while requiring less data and fewer computational time. But, and this is a big but, physics-informed neural networks dispense with the vanilla formulation of Racy et al. In 2018 are quite difficult to train and even not effective in complex cases. Anyway, this idea of regularization based on physics is interesting, and we can use it to improve data-driven approaches based on neural network, particularly when our systems are not described by PDs, but by simple physics model. And finally, graph neural networks are a promising architecture to model complex physics in large data problem, but still more research work is expected and needed in this area. So this was a brief comment on our work in this area. And as I said before, you are very welcome to contact me, to contact us for more information about this approach. And also, if you have a similar problem, probably we can help, at least by providing hints on what didn't work for us. Thank you very much. Muchas gracias por vuestra atención y bueno, queda a disposición de las preguntas que queráis hacerme.
Bueno, muchas gracias, Juan. ¿Nos escuchas bien?
Sí, te escucho, Luis.
Vale. Creo que, bueno, primero saludarte ahora en público, ¿no? Es un placer tenerte con nosotros y creo que tenemos preguntas en el chat. Sí, Astrid, que también quiero agradecerle a Astrid que ha organizado esta sesión. Astrid, si nos puedes ayudar con las preguntas.
Sí, de momento solo tenemos una consulta en el chat. Rodrigo Varía te pregunta, Juan, you said that regularization was to include the fighting residuals. Then what is soft regularization?
Yes, that's a matter of terminology, in fact, because I use the term soft regularization when talking about this is the limitation of pins. This is the terminology used in the paper by Krishna Priyan and collaborators. They say that the regularization introduced by PDEs is soft. It is soft in the way that they define their the loss function in their approaches and also the activation function that they use. But in general, I would say that in our works, we are also fitting, in most cases, we are fitting residuals, and we are using the residuals of the PDEs for the PDEs or the physical model for the for adjusting or for this additional term of the loss function of the hybrid models. Hope this answer more or less the question.
Okay. De los presentes, ¿alguien tiene otra consulta que hacerle a Juan?
Yes, we have a question here from Theo.
A ver, no sé si te escucho.
Closer to the line.
Ah, sí, vale, sí, estaba cerca del
Can you hear
micrófono.
me better now?
Sí, te escuchas bien.
Okay, now I can hear you.
Okay, you can hear me, but you cannot see me now.
Yeah.
Yeah, no, you mentioned that the formulation of like pure physics-driven neural networks without any data, they are hard to train, but also that the architecture is the most, it's one of the most important factors for the performance of that.
Yeah.
What if you experimented with different kind of architecture, for example, with graphs, because you also said that graphs, neural networks are good in the large data.
Yeah.
Possible to do that without any, or it makes everything more complex. Thanks.
Okay, well, very good question. It was also well, I was very shallow on this explanation, and you are right. I say that well, we need additional architecture for pins, and this is particularly clear from the results that we obtain in this paper about the advantages, limitations, and also the opportunities of pins. That work is very focused on pins implemented with CIAN and following the what I call the vanilla proposal by the original paper by Racy and collaborators. And in CIAN and also in this proposal, they use feed-forward networks. So when we try to use feed-forward network, we used very deep networks, and still they didn't work very well. So they work better as we increase the size of the size or the granularity of the mesh for the points of the problem, and also the number of layers on this architecture. So actually, our conclusion was that we need something with temporal aspect or something more complex here. So this is why we left this approach with these vanilla pins, but took all that we had learned about regularization to our own implementation in which we can use any architecture, but we focus on the definition of the loss function. So in this regard, we had the problems that I have presented, the one with the buildings and the other one with the power generation with the wind turbines. They don't use very complex architectures, but GNNs, graph neural network, with custom loss function, which is what we are trying to use in our last iteration on the last application that I have presented here, is for me it is the way to go. So as long as CIAN or other framework provides support for more complex architecture, this would be a good way to go. If not, it is better to tweak your own implementations and to use this more complex network architecture. So this is the long explanation about why I said before, we need more complex, but we don't have them, but we have them, and then this is more or less the evolution of the field and also our experience in the area.
Okay, muchas gracias. Luis, sí, dale.
Do we have more questions on the chat or?
No, en el chat no hay más preguntas.
Okay. Awesome. Well, I think that we share the same experience on trying to use pins and being frustrated because they don't work in some cases, no? So it's good to share the same negative result.
Yeah.
And we have been thinking actually on this topic on the network, no? I don't know if you have any experience or any intuition, if not, or for example, if we should move to convolutional neural networks or recurrent neural networks, because these are PDEs in particular are equations that are unfolding in time, no? So maybe the problem is that we are trying to address the problem in a setting that is actually not the most suitable one, no? But so do you have any experience particular around that?
Well, clearly the pins in the sense that we are talking about them today, they in general don't work very well out of the box for any problem, particularly if you have a difficult problem. And in my experience, for particle-based problems, graph neural network work quite well, despite not using, even though if we don't use physics regularization. I think that the way to go could be this one, combining, instead of using feed-forward networks and then having these two loss terms, having more complex architectures. We are getting good results with GNNs with molecules in general. So, but this happens because the problem is it is very straightforward to model the problem with GNNs. So it depends on the problem. You can use GNNs for defining the mesh of your problem, and then using this kind of architecture. But I'm not very sure if they will work very well, because actually GNNs have additional problems related to gradient vanishing and with other, let's say, stability problems when with different in different problems. I'm curious about this temporal graph neural networks, if they are suitable for this kind of problem. My guess is that they are completely overkill for simple problems. This could be a good way to continue the investigation, and otherwise, until we have a more advanced framework for combining different architectures and pins, I would go with custom implementation and tweaking loss functions and trying to make it work. This is not easy because it requires quite good knowledge of physics, mathematics, maths, and machine learning. And well, this is not always easy to get together in the same team.
Awesome. Thank you very much. I think this is where the problem becomes interesting for the machine learning people, no? Because I have the impression that things are like guns, no? That is a very nice idea, but then when you try to use them, they are actually like very unstable to train. No, they are not the robust method that is going to work, and you just need to. So we see only the tip of the iceberg that works, not the whole iceberg. So in that sense, it's also that makes it a very appealing topic, because I think it's also, to be able to include the two sources of information and all of that sounds, I mean, it's cool, but then it's also very brittle to train. Also,
Okay. Okay, don't get even started with guns. It is another topic in which we have also, let's say, assorted experiences. Some of them good, and most of them not that good, because, as you say, they are very nice on paper. They are quite elegant. In principle, they can be applied to different situations, but the transfer to real problems, the same that happens with pins, is not that straightforward, and also you usually face these convergence problems and stability and problems that you are trying to avoid with these configurations. Not only do not disappear, but are even worse with this kind of architectures.
One, we are regretfully running out of time for the presentation. I think that we need to talk more, because we have a common topic here of interest, and we are trying to both address this problem and also apply it to different contexts. So, for example, is a PhD student is applying this to modeling stellar atmospheres. So there is an astrophysicist and secret in the machine learning game. So we are applying this also for modeling ocean ecosystems and all of that. So maybe there are opportunities for collaboration. Awesome. Well, thank you very much.
San Luis, thank you.
Muchas gracias. Thanks to the people attending online that you have. You know, we broke the record of the inscription to the Inria Talks today, Juan. So you are a superstar. So thank you all and see you in the next meeting. Bye bye. Bye bye. Gracias, Juan.
Gracias. Buen día.